Okay. Yeah, maybe just wait a few, 2 or 3 minutes. So if you have questions, you can ask me now. You can just unmute yourself and start talking. Okay. So now there are 14 students. I will start. So last Wednesday we covered a little bit about the recurrence and transient for mob chains. So we will continue this and start on the stationary distribution or stationary measure today. So I will just start. You have questions, you can ask me during the class or after the end of the class. Questions? Okay, so I will start. Okay. I just open a new document. Okay, so let's start. So last time you already mentioned the definition of like recurrence, transience, etc., right? And also closed set, closedness, or irreducibility, right? Closed set or irreducible set. So etc. So how do you say that? So let's just give you an example, right? Let's just give you an example, which is also the example in the textbook. But before that, let's just recall like two basic theory. The first is let's just recall. The first is the characterization of recurrence, right? So as I said, right, recurrence, they say Y is recurrence, Y is recurrence, recurrent. So if only rho Y actually equals to 1, right? So rho Y is just you're starting from Y and you return to Y truly infinite time, right? This is recurrent. And we have a characterization of Y is recurrent, which is this. So we're starting from Y and we compute the conditional, we compute the average or the mean time returned to Y, right? So if this is infinite. So as a definition, right? So as definition, so EX and Y. So what does this mean, right? So this means you're starting from X, and you compute all the time you return to Y. You return to Y, right? This is the definition of this quantity, and so I just want to compute a little bit because we will use this, right? So what's this, right? What's this term? So this actually is we can use in Fubini, right? Not Fubini, or we can use, yeah, it's Fubini also. So we can use the monotone convergence theory and write this and that. So this is indicator function. So what does this means, right? So this is just the probability is starting from x and ends with y and n steps. So this is exactly this Pn xy. So Pn xy is the shorthand notation. So I'm not sure we introduced first, but so definitely in the fourth edition is introduced. So it is the probability you're starting from x, and you ends with y and n time. Right? So this is the definition. Okay, so this is the one computation of this very important quantity. We will use this quantity at a certain time, right? So this is just one computation, right? Just by definition. So there's another one. Okay, so there's another one, right? So let's compute this. There's another interpretation. So which is the following, right? So this is an integer. This is an integer value, right? So it can be 1, 2, 3, or it can be 1. No, it can be 0, right? So this can be 0. It can be 0, 1, 2, 3, etc. Right? It's the number of visits to y, a number of visits to y. So when we compute the expectation, so it's just. So, I mean, if we just compute then, what's this, right? So we just sum up, right? We just sum up with k and the probability, right, starting from x and ny equals to k, right? And we sum up from 0 to infinite. So this is nothing, right? I mean, 0 really doesn't matter, right? K equals to 0 doesn't matter. So this really equals to 1 to infinite. And this is k px ny equals to k. Right? Just definition of expectation. And you can compute, or you can check, right? The following, we use this several times. So we can just rewrite as the sum of the probability of the level set. You can check, right? You can check, right? Simply by absorbing this is the probability of k minus probability ny is bigger than k plus 1. And you just telescoping that, and you can find this. Why we write in this form? Because this form is good. And we can rewrite this. So this is just starting from, let's just write one more step. You're starting from x, and you return to y and list k times, right? So since it's at least k times, so this should be finite. This should be finite. So by a theory before, so this is just row x, y, right? You first return to y, then you visit a y, k minus 1 time. And if you sum this, right, you get row y, y, right? So that's why, right, by this computation, we have the following story. That is y is recurrent. So let me go back. Let's don't write here. So by this computation, so we have the following. We have the following characterization, right? It's here. We have the following characterization, right? So if y is recurrent, as long as you're starting from y, and the equation of the number you visit y, right, is infinite. Okay, so but if you but this does not mean so if you're starting from other point, this is not true, right? This is not true. If you're starting from other point, this might be 0, for instance, right? Because you might not enter y, right? You might not enter y. You're starting from a certain point x0, you might just stuck there, right? You might cannot reach y. So the number of to y is 0. Just a basic recall of what we did in last lecture. Okay, so let's just recall, right, what is closed, right? Let's just recall what closed means. Right? What C is closed. Of course, right? Of course, we do everything. We do everything on S. Right? This is a state space. This is a sigma field, and we consider all our Markov chain. Right? So a priori assumption. This is our setting, right? So this is our setting. So we call C, right? Because C, of course, is a subset in S. Because C is closed, right? So if the following, right? The following. So what does closed means, right? Closed means if you're starting from X, if X is in C, right? So then, and you can reach Y from X. So that means, right, infinite time, right? So then Y is in C. So what does this mean, right? If you're starting from X and you can reach Y, you can reach Y, right? Y is accessible from X, then Y is also in C. Then Y is also in C. So C means, right, if two states are accessible, right? So if one is there, then the other is also there, right? So it's closeness. You can easily check, right, as I told you. So if you're starting from X, so X is in C, so then all the paths actually is in C for all n. So if you're starting from X, right, so then all your trajectory, all your paths will stay in this closed set C. Okay, it's closeness. So there's another notion called irreducibility. Irreducible. Let's call D is a set, right? D is irreducible if the following. So if X and Y are both in D, so then rho XY is bigger than 0. Is bigger than 0. So what does this mean, right? So this means, okay, so if you have a set D, you any 2 point X and Y, so then it's accessible, right? You can go from X to Y, right? So which means, right, rho XY, you're starting from X and infinite time you can reach Y, right? So this means, right, infinite time can reach Y with a positive probability, right? So it's a notation in probability. Okay. I give you several examples in last lecture, but let's see one more example. Okay, let me. Okay. Okay. Let's see one more example. Okay. I will try. I will try another. I will try to connect to my iPhone. So because I take a picture there, so I can save some time. Okay. let's say stop share and share screen iPhone. Share, trust, not now, trust, trust. Oh, I cannot let you see my, but that's bad, right? So, okay. So I'll just show you this, right? So, so because you can see the you can see the example in the textbook, right? Okay. This is our. Okay, you don't have questions. You can airdrop it to iPad. Oh, yeah, 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 that's clever. Okay, yeah, we try next time. Yeah, I should change my password. Okay, okay. So we have showing this, right? So if C is closed and if C is closed, then C has a recurrent state. So, but we need C is finite. Right? So this is a theory we showed in last lecture. I just tell you how to show that. I didn't show the details. So if C is a finite and a closed set, right? So then C has a recurrent state. Right? C is further irreducible, right? Is irreducible. So then, so any state in C is recurrent, right? You can see the examples. You can see the examples to. You can see the example in the picture. So now it's called 7-state chain. It's called a 7-state chain. Yeah, yeah. I will try to follow your advice. I will try to using AirDrop. Screen sharing. Okay. Okay, so yeah, it won't be hurt, right? If you just write a little bit more. Yeah, I mean, it will be slow, but anyway. So okay, so what's so okay? Maybe I just write that. So this is the example in the textbook. So it basically is just a little bit more complicated than the example I give you in last lecture. So yeah, AirDrop, iPad. Okay. Drop. Okay. Not here. So AirDrop. Hard to find that. I don't find that. Mhm. Yeah. Anyway, I just I try to figure it out next time. Or maybe. Uh, yeah, maybe I show in my.
It might be in photos.
Oh, okay. Yeah, that's yeah, but it's very bad to show photos, right?
Okay.
Yeah. So Okay, now I can show you in just in the Mac in Mac. Uh, okay. Okay, so let's just show in my Mac. So, so let's see. Not here. Oh, it should be in Note. It should be in Note. Okay, it should be in Note. So let's share the screen. Share screen and new. Can you see that?
No.
Resume share. Okay, now maybe you can see that. Right.
Yeah.
Okay.
Yeah.
So okay. So this is just the example in the textbook. They have 7 states. They have 7 states like 1, 2, 3, 4, 5. Right. So this is the transition probability. So if they have self transition, we just ignore that. Okay. So it's very easy to determine like the recurrent states and the transient state, right? So there's a very intuitive idea, as I said in last lecture. Okay, so if you're starting from, for instance, right? So one, right? One actually is a recurrent state. So why? Because right, you can see, right? So this state you can move to the left. So from one, right, you either goes to yourself or you go to 5, right? So for any mass you send to 5, you can always return to 1. So there's an explanation. So if y is recurrent, which means right, you're starting from y, and wherever you go, you always can find a way of coming back, right? So this is also true for 5, right? But this is not true for 2, right? So 2 actually is transient. So why, right? So you can see, right? You can think, right? There are many masses, right? The mass in 2, and their probability going to 1, going to 4, and going to 3, right? And it never comes back, right? Like if you go to this block, right, you never return. If you go to this block, you never return, right? This is also the same for 3, right? So T is a transit, right? You can analyze other states as well, but if we just using if we just using the discussion in the textbook, right? How to do that, right? So we can also determine like 2 is is transient. Why? So you can assume, right? If 2 is uh, recurrent, right? And row to 1, right? From 2 to 1, actually this is positive, right? This is positive. So since recurrence is contagious, if 2 is recurrent, then 1 should be recurrent as well, and the transition row 1, 2 should be positive, or should be 1. Right? So row 1 from 1 to 2 should be positive, should be 1, but this is not 1, it's 0, right? You cannot move from 1 to 2. Right? So our assumption is not true. So T is transient, right? So you can use in the recurrence is contagious to argue that as well. Okay. So let's screen has stop and share. So let's see. Let's just go through quickly. Let's just go quickly what we did last, or we almost did in last time. Um, Okay, let's show one more. Um, so share. So can you see the share?
Yes.
Okay. Okay. So this is we summarize the example. So in the example before, right, what we did, right? So for instance, there are two possibilities, right? So one possibility is okay. So we consider all the possible x, right? So if rho xy is bigger than 0, then we should also have rho yx is also bigger than 0. So if this is not true, right? For instance, there exists a y such that rho xy bigger than 0, but rho yx equals to 0. In this case, we can get x is recurrent directly, right? So it's just the previous example with x equals to 2, right? X equals 2.
X is transient.
Yeah. So if we have x, right? So which rho xy is positive, but rho yx is 0, right? So then x is transient, right? So then that case is very easier, right? So now we consider this case. So if rho y is bigger than 0, then we should also have rho yx is bigger than 0. Right? If you can go to y from x, then you can come back, right? You can come back. So actually, right, so if you consider those type of x and write everything, right, you can reach from x, right, because it's cx. So then this set actually is irreducible and closed, is irreducible and closed. So so this is just a basic idea how to prove that, right? So this is our x. So if you can go to y, so first let's show irreducible. If you can go to y, and also you can go to omega, right? So then this omega and this y and omega are accessible from each other, right? So then rho y omega is bigger than 0, right? So this is very easy to see. Like y, right? So because rho y omega is bigger than rho y x and rho x omega. So this is a homework problem. It's called strong Markov. It can be proved by strong Markov problem. So rho y x is positive, right? Since y is in this set, right? Rho x y bigger than 0 implies rho y x bigger than 0. And rho x omega is bigger than 0 because omega is also in this set, right? So this we get, by this we get irreducibility. And also, right, so we can show it's closed, right? Closed means, right, y is there and omega is accessible from y, right? Then rho x is bigger than 0. It's the same story, right? So if y is there, right, this is positive, right? Then we can show this is positive as well. Right, so what does this mean, right? This means if you have Cx, right, so this Cx, you have X, you have this property, right? So then this set is reducible and closed, so for instance, if this set you know is finite, right? So then this set actually is captures all the recurrent state, capture all the so all the state in this set is is recurrent. Or if you know there's one state in CX is recurrent, right? So then it's all recurrent. Okay, let's stop sharing and let's open another set. Okay, I think let's go back to the iPad. Share screen. Okay, so yeah, so now let's see more examples. Let's see more examples. Last time I told you to read the MG1 model, MG1 model. Okay. Um, okay. Okay. So, so let's just before then let's recall the last theory is decomposition. We stated earlier last time decomposition theory for Marvin. So what does this says, right? We write everything R. We write every R, which is the recurrence, all the recurrent state, all the recurrent state. So then we can decompose. So then we can decompose those set. So then we can decompose this set as the union of Ri. So each Ri is closed and irreducible. It's closed and irreducible. So actually those those Ri, the proof is easy. So I will skip that. So actually each Ci is each Ri is just a Cxi. So Xi is a recurrent state, and we capture all those Y which are accessible from Xi. So Xi is recurrent. So Xi is recurrent. You can so why this is true, right? Why this is true? The idea is exactly like what I just told you. So you can show the following. So Cx, so either so this is empty or they are equal. So if both x and x tilde are recurrent, right? So then so they are either so the cx tilde, right? So either equal or has no intersection. So the proof is exactly like what I told you for the previous discussion. Okay, so I will just skip that. So
I have a question.
Yeah, go ahead.
So you in this decomposition, you have missed the transient states.
Yeah, you're right. So this is the decomposition of the transient state.
No, but you have like if you write this R is equal to union over Ri where each Ri are closed and irreducible, then the transient states would not be captured in any one of them, right?
What do you mean?
I mean, there are
It is the
transient states.
Yeah, they are
decomposition
possible
of
transient states, yes. But this is the decomposition of all recurrent states.
Oh, this is the decomposition of all recurrent states. All right,
Yeah,
all
yeah,
right, all right.
yeah. Maybe just add a few comments. Yeah, I should always use iPad. I shouldn't jump, right? So if I jump, it's more, becomes more hard to make it coherent, right? I should always use iPad. If I want to show you something, I just show you something, right? So, but I should keep one document. Maybe that's better. Yeah, and also easier. Okay. Let's just call this remark. And this is a theory. The theory, you can prove this, right? You can prove by strong Markov property. So which is exactly I told you is this, right? So rho x, y, so it's bigger than rho x, z, rho z, y. Yeah, you're right. Yeah, I'm right. So let's say if from x and you reach y in finite time, and you can decompose this, right, to z, right? You first reach z, and you reach, you're going from z to y, right? You're going from z to y. Definitely true, but this is exercise, right? You can try to prove this, right? This is just you starting from x and you return to y in finite time, right? And this is definitely bigger than you starting from y. You first reach z, right, in finite time, then you're starting from z, you reach y in finite time, right? So we just use this property. Okay. Yeah. Okay. So I will give we'll talk a little bit about branching process. Then I will, so let's talk a little bit about branching process. So branching process is one example, right, of Markov chain. Okay. So in branching process, but so classically, right? So we just treat this to be one, but maybe you can. So but here, right? So we can treat let's say zx can be a general integer, right? So it's an integer. It might be not one, right? So you have several individuals in zero generation. Okay. So let's assume rho 1, 0, right, is positive. So if rho 1, 0 is positive, that means, right, so you starting from 1 and so this is the probability. So which is the probability of no children. Of no children. So this is positive. And so if this is positive, right? So if you starting from k individuals, right? So this by independence, this is just this. You take the multiplication, and this is also positive. So, but if you starting from 0, right? If you're starting from 0, you always get 0, right? You cannot, because the branching dies out, right? So this is 1. And if you're starting from 0, this is always 0 for k equals to 1, 2, etc. Right? So if you write if you draw a picture, as this is 0, right? 0 state, right? This is k, it's k state, right? K is bigger than or equal to 1. So this is a probability, right? Rho k 0, rho k 0. And so if you reach 0, right, you always return to yourself, right? You always return to yourself. Okay. So this state, so this actually is recurrent. So 0 is recurrent. The 0 is recurrent. So why? Right? Because you cannot send any mass out, right? So you always stay 0. And 0 is not just recurrent. So 0 is also called absorbing. So let's just so 0 actually is a absorbing state. Absorbing state. So which means, right, once the chain enters this state, it always stays there, right? So absorbing means what, right? So absorbing means so once the chain enters 0, it remains there. Forever. It remains there forever. Okay, so 0 is recurrent, and not only recurrent, is absorbing. So this is a transient state. Right? This is transient. So I mean, this is easy to understand, right? So for this amount of mass, right? Once you reach 0, right, it stays there, right? This amount of mass, once you reach 0, it stays there. And also you can think, right? So if this is recurrent, right, and this is positive, right? So this transition probability should be positive. From 0, it should be positive, but this is not possible, right? Because 0 is absorbed, it's an absorbing state. Of course, this is an easier example, right? It's an easier example. So if we have, if S is, let's say S is infinite, so, and also irreducible. So then either all states are recurrent, either all states are recurrent or states are transient. Right. So this is simply by contagious. Right. Since the state, right, since chain is reducible, so if one is recurrent, then all states are recurrent, right? Or if one state is transient, then all state is transient. So you can think this, can see the simple random walk. You can look at a simple random walk, let's say on I mean on ZD, right, on ZD. Right? So definitely, right, each state is accessible. For simplicity, right, we can just think like very easier. Let's just think in 1D case, right? -1, 1, 2, right? So if let's say you're starting from 0, right? You have 1/2 probability going to left and 1/2 probability going to right. Okay, so so definitely, right? So each state, right, is accessible, right? If you're starting from J, starting from I, right? So you can definitely reach to J, right? In certain steps, right? So the Z, right? So Z is the state space actually is irreducible, right? Is irreducible. So if you can show, right, the random work 0 state is recurrent for simple random work, then so all the states are recurrent, right? In this case, we can just say, right, this random work is recurrent or transient, right? So if the state, right, the state space is irreducible, we can just call, right, a Markov chain is recurrent, transient, right? So instead of just say one state is recurrent or not. So as I told you in last lecture, so let you to choose this example, right? Because we use this example a lot, but I will just go very quickly of this example. Maybe I will just mention a little bit because we don't have time. So this is a very interesting example, right? So what this means, right? This means Markov. M means Markov. This means the number of arrivals let's say is satisfies a Poisson distribution. So what does this model used for, right? So we use this model like to modeling, right? That you have a lot of people coming to a server and you're waiting there to get served, and each custom, so the number of arrivals of custom satisfy Poisson distribution with them. So Markov basically just means, right? So the number of arrivals in different intervals are independent, right? So they basically means independent. Okay. So G here means general. G here means the service. So it means the service time satisfy a distribution. So F is a distribution. So for each the service time satisfy a general distribution, right? So it's F. So here basically just means, right, there's only one server. So every people are waiting there to get served, right? It's like you get you queuing for get served, or in supermarket or something. So just one model. So in example, right, in this example, we write xn as a Markov chain. So xn so is just the number of customs. It's a very weird definition, but this really makes sense. But you need to spend some time to get used to that. So it's a number of custom in the queue, and the time, the nth custom. Nth custom is enters service. Enters service. Okay. So it might take a lot of time to just, but let us still do that, right? So it's the number of custom waiting in the queue and time the nth custom enters service. So to you can read the you can look at the photo, right? You can look at the figure in the text, but I won't show more. I will be quick to tell you a very fast version, like to understand this model, since I don't have any time. So there's a faster way to understand this xn. So this is okay. So let's let's say let's write AK. So AK is the, what is AK? So AK is the probability their K custom arrive. So I'm just write AK. So since the number of arrivals satisfy the Poisson distribution, and the service time of custom is according to FT. So this is a probability. So this actually the probability that K customs come, custom arrive during a service time. So K, of course, right? K can be 0, 1, 2, etc., right? And each Kasai I, so we write each Kasai I satisfy the distribution which given, so Kasai I, the number of the K minus 1, so P which is given by AK. So what does this mean, right? Psi I is actually so the number of customs, right? So the number of customs, so the number of customs to arrive during the ice service time. So this is the number of custom arrive, right, when the ice custom gets served, right? So the amount of time the ice custom serves, so the number, the total new custom comes. And also you minus one, right? So minus one. So this one means, so the custom complete the service, right? This is the custom complete the service. Complete the service. So the probability, right, of psi I equals to k minus 1 is given by ak, right? So k, of course, k equals to 1, 0, right? 1, 2, etc., right? So what is xn, right? So what is xn? So let's set x0 equals to x, right? X is an integer. So then xn plus 1 is just equals to xn, right? So the original amount of custom waiting and plus the new arrives, right? So this is the new, right? But we should, sorry, so this the original number getting served, right? So the original number of customs in the queue, right? So this is the total change, right? After one service time, right? So this is the new number of customs in the queue. But sometimes, right? So this can be -1, right? So, but this cannot be -1, right? So we put a positive part here, right? So if xn 0, right, so this is -1, right? So we just take 1, right? So this is the definition. This is our definition. This is our definition. This is so you can read all the discussion in the textbook, right? But there's one very intuitive explanation of this G1. So how to explain that? So it's something like this. Okay, so let's say we have many customers are waiting in the queue, right? In the queue. So this custom now get served. So this custom now is served. So let's say this is n custom gets served, right? So this is the total number of people waiting there. The total number. So this number actually is just xn. Okay. So you might feel unsure about that, but you go to take that, right? So I can tell you, right? This is just xn. Right? This is the total number of people are waiting. Right? So these people, this person is already get served, right? So this is the total number waiting the queue. So in the period, right? This guy getting served, right? So there are new people comes, right? So there are new people comes. So let's assume, right? So there are new people comes. So this is this actually is just psi n plus 1. This is psi n plus 1, not just psi n plus 1, right? So this is I think this should be so wait let me make sure, right? So if there's a -1 issue, right? I don't want to make mistakes. I don't want to make mistakes. Okay. Okay. So if this is xm, right? If this is xm, this is cosine n plus 1. So wait. I think this should be. I think I should change. So this is the number in the line, right? So I'm not sure. Okay, I don't see it. I think my previous session is true. Okay. So this is xn. So if this will get served. Okay, yeah, I'm true. Okay. So this is xn. This is xn, right? So this guy served, right? It doesn't count. And this is the number of custom comes during the service time of this guy. And so what is xn, right? So xn plus 1, right? It's really xn. The people are waiting, right? And plus cosine n plus 1. But here, if we should plus 1 here, right? So this is the number of people arrival, right? And as I told you, right? So this number can be negative, right? And so why, right, it's now is minus 1 here, right? Because when n plus 1 custom, because when this guy gets served, right, this guy gets served, so there are this many of people, right, this many of people there, right? So we need to minus, right, this plus this, then minus 1, right? So that's why we get this, right? That's why we get this number. So, but sometimes, right, this can be -1, right? So that's why we put a positive sign there. Okay, so this is true now. But we can think, right? We can think like the following. So, okay. So how to think this process, right? How to think this Markov chain Xn, right? As I told you, right? So there's a intuitive, right? Let's explain this intuitive way, right? To see, right, if it's recurrent or transient, or which state is recurrent or transient. So, so this new arrivals, right? These new arrivals. So these new arrivals, you can think this xn as a branching process. So this is like a parent node, right? So these are children of this individual. So when this person gets served, or this individual gets served, all the new arrivals during the service time for this guy can be viewed as the children of this guy. Okay, so then, right, so for instance, if this guy gets served, right, so there are new people comes, right, there are new people, new custom, right, let's call this, right, and this is cosine n plus 2, right, plus 1. So this custom, those customs can be viewed as the children of this guy. Okay. So then we can just use the previous, we can just view xn, right, the mg1q as a branching process. As a branching process. And so by our discussion of branching process, this parameter mu is important, right? So this mu is important. So what is this mu? It's A0, so AK times K, AK times K. So K from 0 to infinite. So this is the mean value of customs. Mean value of customs. Mean number. Mean number of arrival of customs. Arrival and service time. Right. So for a branching process, right, there's a question of like mu bigger than one. So mu bigger than one. So for mu bigger than one, right? So we know, right, it won't dies out. And for mu is less than one. So for mu is less than one or equals to one, right? So the branching process will eventually dies out. So eventually dies out means, right, everything, if I use the end, it will reach zero, right? So, but if mu is bigger than one, so this is not true. Right? So using that, we can conclude, but it needs some argument. So if mu is bigger than one, right, it's transient. It's transient. And if mu is less than one, so okay. So if mu is bigger than one, if mu is bigger than one, so if in this case, right, if mu is bigger than one, how do we do that, right? If mu is bigger than one, so we're starting from x customs, and we consider the probability, right, it will reach zero, right, it dies out in finite time. So this A, right, so it's just rho to x. So why is rho to x, right, just by independence, right? So where rho actually is, rho actually equals the probability, right, it will dies out. It will dies out. So rho actually is a probability of Zn equals to zero, right? So we're starting from one, z0 equals to one for some. So rho is the probability, right? You're starting from one individual, right? The branching process dies out. So, and from a theory proved earlier, so rho actually is the unique solution of rho equals to phi rho. Phi rho is in this T is in 0, 1, and phi is a generating function for this branching process. So phi t is just we sum up k equals to 0 to infinite and t to k. So anyway, rho is a probability, it dies out, and this is less than 1. So this is less than 1. So this is definitely less than 1, right? So this is definitely less than 1. So, right, if you think about that, right, so we have x, we're starting from x, and it have positive probability you reach 0, right? So it's rho x0, right? You have positive probability you reach 0. And but 0 is absorbing state, right? It's absorbing state, right? So x actually here cannot be recurrent, right? So x, so actually transit. So actually this is transit. right? So for mu, for this case, right, so actually is transient. But for mu, but for this case, what is recurrent, right? So we need to say a little bit more. So why this is recurrent? Why this is recurrent? Why this is recurrent? Let me see. Let me see. Okay, how to see that? How to see that? So okay. So does anyone know how to explain this? It's very easy to explain, but do you know how to explain this? So this is for the XN, right? Not a branching process. We're using branching process to explain this. So okay, it's kind of so for this case, right? Mu bigger than 1. For this case, mu bigger than 1. So what we know, right? What we know is that, right? So let's say if you study from X, right? You study from X, you have certain probability you go to 0, right? Certain probability goes to 0. So then Y is transient as well, right? So so of course, right, for branching process is transient. So now we are considering xn, right? So not really the branching process, right? So it's a little bit different. Yeah. So is here, right? So let's say we're starting from X, right? Definitely, right? So there are probability, right? You can reach 0, right? There are certain probability is big O, this is positive. But okay, let's say at a certain time, right? So at a certain time, xn, let's say equals to 0, right? But of course, later you can be xn plus 1 equals to k as well, right? Right? Okay. Again, right? So for this case, right? So definitely all branching process will dies out, right? But of course, again, right? This is not really branching process because their custom comes, right? So their new custom comes. So this CASA I, right, can also be right 0, 1, etc. So if you dies out, for instance, in this case, so the branching process dies out, it can dies out, right? But once you reach 0, you can still move from 0 to any other point, right? You can move 0 from any other point. So actually, this is like recurrent. This is irreducible, right? It's reducible, irreducible chain. Okay. So we are not done yet. We are not done yet here, right? But yeah, it seems not. I think it's not a full explanation. Okay. Yeah, we may still go back to the discussion there to see the full picture, right? Yeah.
I'm
Yeah,
confused. If mu is larger than 1, it doesn't have the probability to go from 0 to anywhere else.
If mu is bigger than 1, when is mu bigger than 1? Oh, so I should, so I think here maybe not a very easy to explain, just look at the branching process, right? So why, so I can tell you in another way, maybe go back to see the original proof. I don't see why, if you just see from process, this is transient. Okay, but I can tell you why this is true. So if mu is bigger than 1, right? So if mu is bigger than 1, so intuitively, so if mu is bigger than 1, so then actually our each quasar I is not each quasar I is just mu minus 1. So since quasar I has a distribution which is k minus 1 times k, and we sum up. So this is just a mu minus 1. This is positive. So the process we get is xn, right? So it's xn. So xn actually is equal. So xn actually equals to this. So this psi 1 plus psi n. So before this, before xn goes to 0. So let's define before n, which is this, before this. So this is IID copies, right? IID copies. And since this is positive, since the expectation is positive, and this actually almost surely goes to infinity, right? By strong law of large number. So xn actually goes to, by strong law of large number, it goes to infinite. So you can show the following. So if you choose x 0 equals to x very large, right? Let's say if you choose x very large, so you don't return. So this actually is less than 1. So which means, right? So if you're starting from x, so what is the probability t0? So this is bigger than 0. So if you're starting from x, right, it's relatively large and you can never reach 0. So then it tells you actually recurrent, transient. So okay, so so why, so we need to say a little bit more, but this is basically the idea, right? So if mu is than 1, right? So then, so each increment, right? On average sense is than 0. So xn, right? So we kind of, so if you draw a picture, it's something like, okay, so we're starting from x, right? And we can move, right? So we can move to x plus 1, x minus 1, and here is 0, right? And 0 is one state, right? So it's all the state is 0, 1, it's all the integers, right? So it's starting from something big, right? X, right? And this is not symmetric, right? So since this has a positive average, right? It is more likely to move to the right than to the left. So if you're starting from something big, actually there are some possibility you never go back to 0. Yeah. So but okay, so but in this, right? So but for the case mu is less than 1, you can always reach 0. Right? So you can always reach 0. So this is the difference, right? Then the criticality happens, right? It's just here, right? Just by this. Right? So from 0, right? From 0 to 1, or from 2 to any others, right? It's always true, right? So the bad part, right? So since psi I, right? Since psi I can equals to -1, 0, 1, 2, etc. number, right? So if you're starting from something small, right? If you're starting from something small, there always possibility you can go large, right? But the tricky part is if you start from something big, right? So let's say x, right? You're starting from x, and you want to reach 0, right? If you can reach 0, right, you can reach to others as well, right? Because from 0 you can go to any other point, right? So actually, right, everything is reduced to show something like this. So in this, in the case, mu, the average is bigger than 1, right? So you have, is more likely move to the right than the left. So there are some possibility, right? There are possibility. You can never go from x, right? It's a positive large number to 0, right? So it can only be transient, right? It can only be transient. So since x is transient, so everything is transient, right? It's irreducible, right? So the chain, so the chain actually the state space now is just z plus. So the chain is irreducible. Okay. Yeah. Yeah. This is the idea, but we need to see. So you need to see the full proof. So to make it clear. Okay. So maybe the difficult. I just make a few more comments. So in case you comments. Okay. So let's make a few comments. So first is this, right? So why this is true, right? Why this is true? So why this is true? Why this is true? Let's just okay, make several comments, right? Make several comments. So let's write Sn, yeah, as the sum of those IID random variable, right? So we know each I has positive. So in the case, mu which is bigger than 1. Okay. So by strong law of large number, right? So this by strong law of large number, this goes to E psi I, right? Which is positive, almost surely, right? Almost surely. So what does this mean, right? So this means Sn. So this means Sn goes to positive infinity almost surely. Almost surely. This means this almost surely. And so if you check, so Sn, the infimum part, bigger than almost surely. So why, right? So why this is true, right? Because so this equals to Sn. So let's so actually so the part, right? The counterpart has probably 0. So why? So the counterpart is just the infima equals to minus infinity, right? So infima equals to minus infinity can only happen like in infinite. So this has probability 0. This has probability 0. So this is true. So this is true. So this is true means So what does this mean, right? This means, so there exists a k, which is bigger than 0. It's a large number. So such that the probability, so the infimum Sn, which is bigger than minus k, is positive. So the probability, so let's take an infimum. Let's choose some x which is big, Sn, right? We can just choose is bigger than x minus a, is bigger than delta, right? So we can choose x to be, k plus 1. So this is 1. So what does this mean, right? What does this mean? This means if you're starting from x, right? If you're starting from x, there are some possibilities never reach 0, right? There are some possibilities to never reach 0. So that's what we did before, right? That's what we did before. So what does this mean? This means if you're starting from x, so you have some probability you never reach 0, right? So that means you never reach 0, right? So the stopping time equals to infinite. So this is bigger than delta. Right. So in this state, right, you can never reach 0. So what does this mean? Right? What does this mean, right? From 0, right, you can always reach x. Once you reach x, there are certain probability you can never come back, right? 0 is is transient, right? 0 is transient, and all other states are also transient because they are accessible, right? Because they are irreducible, right? So z is irreducible. Yeah, I don't cover a lot. Yeah, it's a kind of yeah, it's very to talk about one example. It takes a lot of time. I plan to talk about stationary state, a stationary mirror and diffusion in this lecture. I wanted to go through MG1Q first, but this is a very good example. So even you didn't fully understand this up to now, just to go through that. And also there are, so there are many discussions in the textbook. So maybe I will just post my notes shortly because not just these notes, my prepared notes. So I haven't studied on the material prepared for today's lecture because talking about MG1Q takes a lot of time. That's planned, but I need to explain as well. It seems it's better to just follow something instead of yeah. I should just just use iPad and go through maybe self and talk about some arguments. I definitely should skip a lot of things as I cannot cover important stuff, right? So there are some general discussion, general theory in the textbook. So I mean, if you have other things, you can leave the meeting, but I will just write several things. So in the theory in the textbook theory 5.3.8. So it's just summarize everything we did for the MG1Q, and so right there's also the example on birth and death. Birth and death chain I haven't talked about. So it's actually is a very interesting thing, right? It's very useful. But I won't have time to talk about that. Yeah, I won't have time to talk about it. So yeah, and I prepare a lot on the stationary mirrors, but so since we only have one lectures on this part, yeah, we just to talk about stationary mirrors and mention several convergence results for asymptotic mirrors, asymptotic convergence, like as t goes to infinity. Yeah, I will stop here. If you have questions, I can ask. Um, but maybe I will just find many readings and you can take some notes instead of let you do some concrete problems. Because I want to cover, I want to finish many topics, but we don't have time. Yeah. So next lecture, I've just started on the stationary mirror and asymptotic convergence. So yeah, please spend some time for MG1Q and the following discussion on recurrence part. Yeah, if you have time to review, that's better, right? I will try just using iPad instead of showing you a lot, right? Then that makes it hard and not maybe not very easy to follow, right? Yeah, that's it. That's it. You can, if you have other things, you can leave the meeting. If I want to ask questions, I can answer questions.
So for the new homework, we already have a problem on 5.3.4. That's on descent person death chain. Do you think
Oh, which one?
5.3.4?
5.3.4. 5.3. Oh yeah, yeah, you're right. Yeah, 5.3.4. Yes, yeah, I have that. Probably that's not a very hard. We write the formula there. Yeah, yeah. So okay. Yeah. Yeah, I think if you read the following, it won't be very hard to do. Yeah, I should, but I haven't fixed.
So the rho you mentioned, the rho is the fixed point of t, phi t, right?
Row, let me see. Row. So which okay, the stationary, the fixed point, right? This one.
Um,
This
yeah.
one. Okay.
Yeah.
So rho is a fixed point of phi rho.
Yes. So no matter mu is larger than 1 or smaller than 1, rho is strictly between 0 and 1, right?
We should be careful, right? Why rho rho so when we discuss this so of course, right, there's one solution. So rho, if so this has so can be one, right? So the fixed point, so phi rho. So sometimes, right, so sometimes rho, right, if rho equals to one, rho equals one is always the fixed point, right? It's always a fixed point, but we want to seek the fixed point between 0 and 1. So originally, so we want to solve phi rho equals rho for rho between 0 and 1. So it can be 0. But in our case, cannot be 0 because so rho in our case, this case rho cannot be 0 because because A0 is not 0. Yeah. So so the problem is rho is so this is all the case for mu is bigger than 1, right? So mu bigger than 1. So the case if mu is less than 1, I guess so rho actually is 1. So this is the theory. Let me find this.
I think
So this is the theory. So
Go another class.
oh yeah, you can be.
Sorry. Yeah,
Yeah,
sorry.
yeah, go ahead. So this is theory in the process. You can find in section 4.3.4. Yeah. Okay. Let me see.